Okay, here we go. Finding the volume using calculus. Okay, let's see. Let R be the region bounded by this curve and this curve. And then we're going to find the volume of the solid whose base is bounded by that region. And it has cross sections that are perpendicular to the x-axis. And they're semicircles. Okay, guys, when you're doing volume in calculus, you need to first start thinking about how you're going to find the area of the cross sections. Now, a of x is a function that you can use to find the area of each cross section. And then you're going to set up this integral with the area function, which would give you the sum of every cross section between a and b. All right, these guys right here. Yeah, that's your lower bound and your upper bound. A and B, those guys are the lower boundary and the upper boundaries of the region that they give you. The region right now is bounded by these two dudes right here. Okay, so let's get started on this. First, we have to note that we are looking for area of semicircles. Okay, we know that to find the area of circles, pi r squared. So if there were semicircles, we would just have to divide that by 2. You can put the 1/2 in front of it, or you can divide it by 2 like so, however you want. All right, it's important to note that the area function has to be a function of x. And we know that because it says that they're perpendicular to the x-axis. If they were perpendicular to the y-axis, then you would have to write the area function in terms of y. So, this r right here needs to be a function of x. It has to be x's, not an r. Okay, so now let's look at our region, what we got. So here you have x squared, and here is the x function. This is what it looks like. If you didn't know it, you could graph those two functions in your calculator, and that's what you would see. The region that we're looking at is this guy right here. That is the capital R. So this guy is your x, and this guy's your x squared. I'm drawing these lines right here because they represent our perpendicular cross sections. Okay, they're straight up and down in comparison to the x-axis. I'm trying to draw right here a semicircle that's popping off the graph. It's really hard to see if you've never seen it before, but this semicircle is popping off the graph. This line right here, that is the diameter. This is important to note because we're trying to figure out how r is related to my x's. Okay, so if that's the diameter, which we can get by going top function minus the bottom function, then that means x minus x squared would give us diameter. But we don't want diameter, we want the radius. And so if this equals diameter, that means, therefore, r would equal half of that. So now we can rewrite our area function up here with no r. Instead, we're going to write it with x's. Wow. Now we could simplify this. See, I took out the r and I put in the function of r, but I'm not going to simplify it. I'm just going to start setting up my integral. Okay, notice that my lower and my upper bound, it's 1 and 0, and that's because those are the intersection points of my two curves. Okay, so if you didn't know that it was 1 and 0, you can use your calculator to find the points of intersection, and those x values would give you guys the lower and upper bounds. Now, back to, remember when I was talking about perpendicular to x-axis? If we were perpendicular to y-axis, then these two values would have to be y values, not x values. But we're dealing perpendicular to x-axis, and so those are x values. So this is your lower, this is your upper bound, and now let's throw in our area function. Okay, so I'm just copying this dude right here. This is going to be a dx. Don't forget your dx. It's important. That's proper notation. And then right here, we can stop right here, and you just throw this in your calculator. You get your answer. I'm going to go ahead and simplify this dude and do integration just for practice and the sake of it. So if you guys need practice integrating, go ahead and pause this and see if you can integrate this dude, and then look at my final answer, see if you got it. Okay, so I take out the scalar. I'm doing the power right now. So I did the power of 2, I get 1/4, and I have to go x minus x squared times x minus x squared. And so with distribution and everything, this is what I got. And I do some more simplifying by taking out the scalar, multiplying it to the pi over 2. See the pi over 2 right here? I'm going to take this 1/4 out and multiply it to that. That's how I got the pi over 8. And then I have something that's very pretty to integrate. And now I integrate, I get pi over 8 just chilling outside. It's always good to write him so you don't forget it. And then you have 1/3 x to the 3rd, then we have 2/4 x to the 4th, and then we have 1/5 x to the 5th. And then we're going to plug in our 0 and our 1. First I'm going to plug in the 1. When I plug in the 1, this is what it looks like. I just get the same, those fractions right there because those powers don't mean anything when you have a 1. And then, oops, sorry about that. And then when I plug in the 0, yeah, you get nothing because everything multiplies by 0. Okay, so that 0 doesn't matter anymore. I want to keep the pi over 8 out while I find common denominators, add these dudes together. I get pi over 8 equals 1/30, and then that simplifies to pi over 240. That's a really nice answer right there. That's actually exact. If you plug this in a calculator, you're going to get approximately 0.013 units cubed. This is a rounded answer, not exact. This one is exact. Hope that helped you guys.